Hello everybody. Tonight we're going to look at how we calculate an empirical formula when we're given the percentage composition of an unknown compound. It would be really helpful for you to have your calculator available with you, either on your phone or your actual calculator, while we go through this lecture. We learned last week that empirical formulas are the lowest whole number ratio between the elements in a particular compound. All ionic compounds are written in their empirical formula because we reduce the subscripts to their lowest whole number terms. We don't like to use the empirical formula for covalent compounds because that can confuse us as to which compound we're trying to actually work with. However, that being said, when we're working with an unknown compound or something new that a synthesis chemist has produced in the lab, our first step of finding the molecular formula for a covalent compound is to find its empirical formula. So let's get down to this. Please pause for a moment and copy down the steps to calculating the empirical formula. All right. The first step is that if we are in fact given the percent composition of the elements in this unknown compound for a given problem, we can assume safely that we have a 100 gram sample, and then the percentages become the gram value. The second step is for us to convert each mass value in grams to moles for each element in the given compound. Please note, Brinkelhoff does not apply here. Our elements that make up Brinkelhoff are not by themselves. They're part of the compound, so they are not diatomic. Step 3, we divide all the mole values by the lowest mole value to get the molar ratio of each element. Otherwise known as, these are our subscripts. This is how we build the compound, or the empirical formula. We have to be very careful for special decimals when we do this. We may run into an issue where we have something like a 1/4 or a third or a half or 2/3 or 3/4. If we see any one of these special decimals right here, we have to multiply all of the ratios by 4, 3, or 2. So 1/4 and 3/4 we would multiply by 4, and 1/3, 2/3 we would multiply by 3, and 1/2 we would double in order to get rid of it. You can't have a third or a quarter or a half of an atom in a given compound, so we have to get to a whole number. When we have these special decimals, we have to take that lowest whole number ratio with that special decimal and multiply it by a factor, that's all. Okay, lastly, we write the final empirical formula. So I know these rules are a little confusing. Let's walk through them in an example. All right, for this problem, I want you to write down the entire problem, and then I want you to make sure you have a calculator available as well as a periodic table. Here's a typical problem that we're going to encounter when we're asked to determine the empirical formula. We're told that we have some magnetic compound and that it contains 72.4% iron and 27.6% oxygen. Our first step is to realize that we are in fact working with percentages, so we have to assume that we have a 100 gram sample. If we assume that we have a 100 gram sample, then we have 72.4 grams of iron in that 100 gram sample. And we also have 27.6 grams of oxygen in that sample. So that's our first step. We drop the percent sign and we add a G for grams. The second step is to convert both or all of the elements in the given compound from their gram or their mass value to moles. So let's take a look at how we do that. When we look up the molar mass of iron on the periodic table, we see that we have 55.85 grams of iron for every mole of iron. That's the definition of molar mass. Now, if you work this out with your calculator, 72.4 times 1 divided by 55.85, you should end up with 1.30 moles of iron. We're not really interested in significant figures here because we're attempting to get the lowest whole number ratio between these two elements. So our best bet for empirical formulas is to round at the second decimal place or the hundredths place. We're going to repeat this process for oxygen. From the periodic table, we have 16 grams of oxygen for every 1 mole of oxygen. Now, I picked this problem for a number of reasons. The first one here is to show you that oxygen, it looks wrong because we know that oxygen is diatomic. So when we're writing it, we want to put O2, but we have to keep in mind that oxygen is being bonded with the iron somehow, and so it's okay for us just to use O. When we do this math on our calculator, we should get 1.73 moles of oxygen. So the second step has been completed. Let's recap for a second. We took our percentages and we dropped the percent sign and added a G for grams because we're assuming that we have a 100-gram sample. We then converted these mass values to moles of each of the elements. Our next step is to divide the mole value by the lowest mole value. So I hope you can agree with me that 1.30 moles is less than 1.73. So we're going to divide by 1.3 moles, 0 moles. When we do that, we get 1 iron. However, for oxygen, we get 1.33 for oxygen. We cannot have 1/3 of an atom of oxygen. So this is one of our specials. In order to get rid of that special, we have to multiply both of the ratios by 3. So we end up with 3 irons and we end up with 4 oxygens. The final step is to write our empirical formula. Well, since we have 3 irons, we write Fe3O4. Now you might be saying, but Mrs. Smith, there is no iron 4. Well, there is. We just have always stuck with the most common forms of iron ion, the +2 or the +3. The iron can form a +4 charge. We know this because we know that metals can lose 1 to 4 electrons. So in this particular case, we have an iron 4 oxide that happens to be magnetic. Let's recap one more time what we did here, just to make sure you fully understand. We were first given 72.4% iron and 27.6% oxygen. Because we're given the percentages according to our rules, we are allowed to assume that we have a 100-gram sample. If we have a 100-gram sample, then 72.4 grams of it is made up of iron, and 27.6 grams of it is made up of oxygen. From there, step 2 tells us we're going to convert grams to moles of each element. Grams to moles. The third step tells us to divide by each mole value by the lowest mole value. This is where we get our lowest whole number ratio for our compound. So we decided that 1.30 was less than 1.75 moles. When we did this, however, we were able to get a whole number for iron, but we got 1 1/3 for oxygen. This posed a problem. This is one of those special decimals. So in order to fix this problem, and in order to get rid of the 1/3 of an atom, we triple everything. So we tripled. This left us now with 3 irons and 4 oxygens. So our final formula for this magnetic iron oxide is Fe3O4. We're going to do some problems in class tomorrow, so you'll get lots of practice. Have a great night.